So previously we've been looking at sample proportions. I'm taking samples from the entire population, grabbing them together, looking at the mean and standard deviation. Now we want to grab those samples and take their mean, their average, and take a whole bunch of those samples and a whole bunch of the means and put them together. And that's where you come up with the central limit theorem. The mean of a random sample is a random variable whose sampling distribution can be approximated by the normal model. The larger the sample, the better the approximation will be. So a sample size of 30 is considered large enough. So when you're talking about central limit theorem, make sure your sample size is more than 30. So for example, here I have a sample size of 1, 5, 10, 20. What do you notice as I increase in my sample size? Yeah, it's starting to look like a normal model. So again, here's an example visually. So here's my population distribution. If I were to grab random samples from here and take the mean or the average from these, this is what a sample of 5 of those averages will look like. So again, I'm grabbing one, what's the mean? Grab another, the mean. Grabbing 5, grabbing the means, and this will be my distribution, which is 5. Same thing with like this type of population distribution. Here's would be what the distribution of the means look like. This will be the example of the mean of this population distribution, and that is just with 5. Notice when I get to 30, they all look the same. So here's my population distribution, how it's distributed. Just everybody together. When I start grabbing random people and taking the mean, they all become the same when it's about 30 of those samples. Crazy, huh? That's the central limit theorem. Now, this is probably a very important table because there are different formulas for standard deviation. How do you know when to use which one? If we are talking about categorical data, if we were talking about proportion, like we have been, this is the mean we've been using, right? P times Q over N, and take the square root. Now with the central limit theorem, we're talking about quantitative data, something we can measure. We're talking about the mean, average of something. That gives you this standard deviation. Where I already have a standard deviation and I'm dividing, which is the population, and I'm dividing that by the square root of my sample size. Okay? So notice, wait a minute, how do you find a standard deviation when it needs a standard deviation? This is my population. Everybody as a whole, that's standard deviation. So yeah, may want to note on this. With your formula sheet that you can use, those that take an AP test, you will notice that here on the back, you have sample distribution for proportions on the top. So that is our categorical data, like hair color, eye color, etc., left-handed, right-handed. That standard deviation you see here, square root of P times Q over N. Next to that on the bottom you see what? Sample distribution for the means. That's your categorical data. And you see the standard deviation is so. So let's look at one example. A college physical education department asks a random sample of 200 female students to report their heights and weights, but the percentage of the student with a body mass index of over 25 seems suspiciously low. One possible explanation may be that the respondents shaded their weights down a bit. The CDC reports that the mean weight of an 18-year-old woman is 143.74 pounds, with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140. Based on the central limit theorem and the 6895-99.7 rule, does the mean weight in this sample seem exponentially low? Or might this just be a random sample to sample variation? So we were talking about weight. So let's look over here. Weight, is that categorical or quantitative? Quantitative, right? You measure. So we are looking at this standard deviation formula. So I'll go ahead and write here. So sigma square root of n is my standard deviation. Am I given the standard deviation of the population as a whole? Yeah, right? 51.54. And that's over my N. What is my sample size? 200. 200. So, I have 51.44 divided by the square root of 200. We get 3.64. That is the standard deviation of my quantitative data, quantitative data and my means. Now note, I'm basing that on the population. So my mean is 143.74. I want to base this on the normal model. So let's make some checkpoints. Is it random? Let's assume so.
It says random sample.
Does it? Okay, very good. Thank you. Yeah, it's random sample. So check mark. What else should we check? Remember the rules?
If it's independent.
Independent. Are each woman's weight independent from another weight? Yes. Okay, we can assume that. Anybody think of another one?
Success failure condition.
Success failure. Okay, we can check that. So, well, don't have the proportion here, do I? So we'll skip that for now. Remember with central limit theorem, when I'm talking about means, I want a sample size of at least what? 30. And I have, let's say, 200. So we're good there. And there's one more. And that is the 10%. Am I grabbing no more than 10% of the population? Well, let's assume there's more than 2,000 women, right? Or more, we're grabbing the samples. So we're good there. So we'll base this on the normal model. So I have 143.74 is my mean. Going one standard deviation from the left and the right puts me where? 143.74 plus 3.64, 1.7.38, 1.73.74 minus 3.64 is 140.1. So tell me, is this sample of 140 pounds exceptionally low? Or is it pretty close to what we kind of expect? Yeah, it's pretty close, right? It actually fits somewhere around here. So it's within one standard deviation of our population standard deviation. So it's fine. So with central limit theorem, we're looking at categorical data. We're looking at where you have a population standard deviation, and we want to find that mean standard deviation. That is the population standard deviation over square root of the total sample size.